Afternoon and last of the conference. We have Dmitry Melnikov that is going to talk about entanglement and holographic states in Chern-Simons theory.
Well, thank you very much for everybody. It's quite challenging, so it's Saturday afternoon after lunch. And I hope I will not be very boring. And first, I would like to thank the organizers for the opportunity to give this talk and also for making it possible here in this corner of the world. And you should also think of that at least some of them spent 3 weeks sitting in this classroom probably, or standing in this classroom. So it's really hard work. Okay, so what I'm planning to talk about is a certain, well, a quantum mechanics that comes from Chern-Simons theory, from quantization of Chern-Simons theory. And this gives some so what I will try to show to you is that it gives some very intuitive picture description for quantum entanglement and other fundamental properties of quantum mechanics. And this will lead to, while studying quantum entanglement, this will lead to introduction of some special simple class of states. And one of the purposes of this talk is to show how the states are relevant and connected to holographic states, or the states which have classical gravity description. So I'll give a few. So there were a couple of talks here about entanglement, and in particular, Johanna in her talk, she was making connection between entanglement and geometry. And the difference here is that I will describe entanglement in terms of topology rather than geometry. But the connection is not very surprising because Chern-Simons theory is an example of holographic correspondence. So we know that three-dimensional Chern-Simons theory with group SUN, level K, is dual to Wessel-Witten theory, two-dimensional Wessel CFT, SUNK CFT. So, well, this description I will give a few examples which uses this topological intuitive description of quantum physics. And in the end, so inspired by this recent progress in black hole information paradox, I'll try to introduce some model that tries to describe the relevant effects in black hole evaporation in this language. Okay, so this work is based on this three recent papers. And so to introduce this quantum mechanics, it's actually, there exists a very simple category theory definition, which unfortunately by the lack of time I do not want to explain here. But despite the name, it's actually a very simple definition and very intuitive. So instead I will just say that, okay, we have a Chern-Simons theory. So, not sure. Okay. Okay, so this is the action of the non-abelian Chern-Simons theory. So you define a state simply as a path integral with given boundary condition. I'm not sure that's just my, okay. With prescribed boundary condition, so this defines your state. And in particular, if you want to calculate an overlap, an internal product of two states, you have to compute a product of two path integrals and integrate over the boundary conditions. So the particular topological quantum field theory that I will use here in this talk is SU2 Chern-Simons theory with level K. And to define a Hilbert space in this theory, I need to define a boundary for the three-dimensional space, and I will consider a collection of two spheres. So imagine a three-dimensional space which is bounded by a collection of non-overlapping two spheres. So one example, for example, is a sphere, or if you think of this as a two-dimensional surface, so that represents a Hilbert space. If you think of this as a three-ball, then this is a state in this space. That's an example of two spheres, so that's a hollow sphere, so there's internal and external spheres, And the state is the space between the two spheres. You can have also two cavities in particular. That will be a state in a product of 3 Hilbert spaces corresponding to a single sphere. So it turns out if you discuss Chern-Simons just in this setup with this ordinary sphere, then this corresponds to, if you quantize it, this corresponds to a trivial Hilbert space of dimension 1. So if you want something non-trivial, you need to introduce punctures. So you need to introduce holes on the spheres. So if in terms of states, which are 3-dimensional, glued to these boundaries, these punctures will be some lines. So these are Wilson lines of Chern-Simons theory. And here you have an example of a state in the tensor product of 2 sphere Hilbert spaces. So in this kind of Hilbert space. And then this state is described by these Wilson lines that can either end on the same sphere or they can go from one sphere to another. So that's an example of a state. So if you have a minimal non-trivial example, you have to put 4 punctures. Well, this is in case that these punctures correspond to, well, they're classified by charges, so they're kind of non-dynamical particles. And each one has certain charge, which in case of SU2K is a representation of the Katz-Moody SU2K algebra. So the manifold will be compact because you can always think of it as interior of a sphere. So it is so something like this. You have a sphere, you might have an arbitrary number of spheres inside, but it is compact as one of these spheres you can always consider as external one, so it's a compact space. Okay, so the minimum working number is a sphere with 4 punctures, and that would correspond to a Hilbert space of dimension 2. So that will be the qubit. And then in this Hilbert space, you can choose a basis by connecting 4 punctures in a different way. So here I have 2 points in the northern hemisphere and 2 in the southern hemisphere. So I can connect them either in this way or I can connect them in this way. And then this would correspond to 2 linearly independent states. But these states are not orthogonal to each other. So I can introduce the basis by usual Gram-Schmidt procedure by subtracting the second state from the first one with appropriate normalization. So these are the states. So for simplicity, I will not draw spheres. I will just draw collections of points, and I will connect these points in different ways. So in principle, it should be self-explanatory, which well, let's say Hilbert space, which factor of the Hilbert space the points correspond to. So what's the scalar product in this space? You have to glue the surfaces along the common boundary. So in terms of path integral, remember, to compute the scalar product, you have to integrate over the whole space, right, along the boundary. So in order to compute scalar products in this, for these states, in particular, if you want to compute these normalization factors, you need to compute these 3 overlaps. So if you glue 2 spheres along the common boundaries, the space that you will get is a 3-sphere. So you have to, now I have to tell you how to compute the, so that would be correlation functions of Chern-Simons theory in S3. How do we compute them? So we know from Witten that these are Jones polynomials. So how do we compute Jones polynomials? You can use the formula that matrix model that Nikolai used in his talk, but that's not the simplest way, and you cannot compute everything with this formula. So there is a very simple prescription based on the so-called Skene relation. Then the prescription is the following. So if there is just a single circle, well, first of all, if there's nothing, just an empty 3-sphere, then the result is 1. If you have a single closed Wilson line in 3-sphere, you just substitute this by number, we'll call it D. It's actually, in terms of Katz-Moody, that's the quantum dimension of the fundamental representation. That's one thing I didn't mention, that all these lines will correspond to fundamental representations. So spin 1/2. If you have any knot or link in this 3-sphere and a disconnected circle, so topologically not connected to this link, you can also put this factor of D in front of the polynomial. So that reduces your calculation to a simpler knot. So this is already sufficient to calculate these overlaps here. In particular, in this case, it's just d squared. Here's this one circle. This is d squared again. Sometimes you might encounter more complicated cases. You can have crossings in your diagrams. So crossings can be simplified if you use this so-called skein relation. This is in the notations of Kaufman. So you can replace the crossing by a linear combination of a diagram without, well, let's say pair of vertical lines plus a pair of horizontal lines. And in this notation, the parameter d that appeared in the previous slide is a squared minus a squared minus 1 over a squared. And if you want connection to Chern-Simons, so there's another standard ladder used q, and q has this relation to the coupling constant k. So now you know everything about how to calculate any correlation function in this Chern-Simons theory. So one observation that this normalization is slightly different from the standard one of Jones polynomials, and it's different just by this factor of d. So it's a natural. It's natural in some way. It is a natural convention because you can think of just one closed line as a trace of identity operator. So d is a dimension. So if you have just one circle, you want the result to be the dimension of this representation. Okay, so now I set up the stage for the discussion of physics. And first, what is entanglement in this topological picture? Well, so it's not hard to guess that if you want to discuss the difference between entangled and unentangled in terms of topology, you should have either a separable topology. So here you have two sigmas two-dimensional surfaces, and which can be a sphere or any other two-dimensional surfaces. So unentangled state is just a disconnected topology. An entangled state is just connected topology. And of course, there's no surprise for this audience because that's, for example, this is what we learn in the ER equals EPR picture, for example. Well, in this particular setup in Chern-Simons with spheres, with two-dimensional spheres, this second state is not always is not always entangled. In fact, it can be separable if there are no Wilson lines. And this is related to the fact that spheres themselves have trivial Hilbert space associated to them. So if you want something entangled, really, in this case, you need to have Wilson lines. And Wilson lines can either start and end on the same sphere, the same surface, or they can go from one surface to another. And well, this is obviously an identity operator. And using the basis that I introduced before, you can compute that this is exactly the sum of basis elements. And well, this is a separable state, despite the three-dimensional topology is connected, but one-dimensional is not. And you can have a number of intermediate states, and these are typically not maximally entangled. So then there is a question, well, in quantum resource theory, there is this classification of different types of entanglement. Well, it is useful because, well, if you think of different quantum tasks, so you want to do something with your quantum system on a quantum computer, different states or different resources would be useful for different tasks. So that's why you want to have some classification. Well, here there's a natural classification because you can have different kind of topologies. So every topology you might think correspond to a different type of entanglement. But it is not a very interesting classification for quantum resource theory because you have an infinite, in principle, this classification is infinite. You have a discrete infinite number of topologies. So you want to sort of kind of coarse grain this situation. And well, here there's one caveat that I have to mention that this statement actually depends on k. So when k is finite, for any finite k, you'll have some linear relations between states. So not all topologies are actually independent. There will be some non-trivial dependencies between states, but I want to avoid it. So I think I would rather think that k is very large. So at least with the states that I work, I do not have this ambiguity. or k may not be integer. So in this case also, you will not have a finite number of, well, in this case, actually, the dimension will be, of the Hilbert space will be infinite. Okay, so how can we classify? So let's think of some very simple way of classifying. So we have this Wilson line, and we already learned that if we have Wilson line connecting two sides, then the state must be entangled. If there's no connection, it's not entangled. So if you have, for example, well, a pair of qubits, so here you have one sphere and the second sphere and the Wilson lines between them. And here, this is a situation when the two spheres are not connected by the Wilson line. So that's apparently should be an unentangled state, separable state. This is maximally entangled, as we saw already. In principle, there is a possibility that there's a third possibility here. You can actually consider all different braidings of this diagrams, but first, I'm not interested in local braiding. So if I just apply braiding on the left and on the right of this diagram, that's a local transformation. A local unitary doesn't change entanglement, so I can mod out all these kind of transformations. Well, second, you can braid non-locally, so you can try to braid lines points on the left and on the right. That's a non-local transformation. So from the point of view of this slog classification of quantum resource theory, that's not what you want. So this is a non-trivial operation. That might be an entanglement operation. So I just want to mod out all braidings that relate to local unitary operations. So in this case, if you just mod out these transformations, all permutations and braiding, local braiding, then you have only these three diagrams. In fact, this middle diagram is also trivial because, again, because of the fact that, well, not only just the one simple sphere has trivial Hilbert space, but if you have a sphere with two marked points, that it has at most dimension 1. So in this case, you can this diagram is actually equivalent to the first diagram. So there are two diagrams, two independent diagrams, and that's the same as in this stochastic local operation in classical communication. Characterization of the states of all possible states in entanglement classes of a pair of qubits. You can generalize this picture for to higher dimension examples. So Q-trees, for example, what would you do? You can increase the number of points, punctures on the sphere that changes, increases the dimension of the Hilbert space, but it doesn't increase it in a linear way. So if you just consider 6 punctures, that will be already dimension 5. So in order to systematically increase the dimension, to pass into dimension 3, 4, and so on, you need to introduce some projectors. So unfortunately, I will not explain how to realize this projection, but basically, you use the fact that product of spins J1 and J2 gives the number J1 minus J2 times twice the number J1 minus J2 plus 1 number of spins. So these projectors, they are basically projecting on the maximal spin in the tensor product of 1/2, spins 1/2. So in this way, you can also reproduce the classification for an arbitrary number of any bipartition of the system of two systems of the system of spins 1/2. So that will correspond to slog classification, and the number of classes will be given by the number of different diagrams in which you just distinguish like how many points on the left are connected to points on the right, and how many points are connected within the same subsystem. So in this way, different entanglement classes will correspond to different topologies. There's one also subtlety that similarly to the case of qubits, there will be some states will be equivalent, so you can basically vary the topology of the first upper half of this diagram. This is what is done in this picture. So you just focus on the four. In this example, on just the 4 pairs of points on top, and you draw all possible way of connecting the two sides. So these are all possible slog classes. You can also try to extend this to higher number of partitions. For example, triplet of qubits. You can try to draw all the possible diagrams. Well, in this case, given this dependencies, so again, here, for example, you have 2 lines connecting 2 sides, so it means that this diagram is equivalent to the first one. In fact, the first 1, 2, 3, 4 diagrams are equivalent. They all correspond to completely separable states. These are biseparable states, because upper state here, for example, is only connected by 2 lines. So there's only one fully, truly 3-way entangled state here. And you can check, you can compute it explicitly. This is an analog of the so-called Greenberger-Horner-Zeilinger state, GHZ. And you don't find in this classification the W state. So why is that so? Why topology is not powerful enough here? Well, the problem is that the topology is discrete, while the number of the states in this Hilbert space is continuous. So not all states can be captured by topology. But you can use approximation with an arbitrary precision. So this is tolerance that appeared in Robstock, and you can, in fact, this W state can be constructed from this GHZ state with arbitrary precision by action of local unitaries. So you can start braiding the lines here, and eventually you can come arbitrarily close to a W state. So in this case, relating again to Robstock this morning, that's is to say that the W state is very complex in this setup. So GHZ state is a simple state, and W state is complex, and it is tempting to say that this is actually what what the statement that entanglement is not enough means in this case, in particular, from the Susskind's paper. Well, so W state, it will appear later. The slog classification tells you that for 3 qubits, there are 4 different classes, and these 4 different classes cannot be transformed one into another by action of local invertible operations. So in this way, the 4 classes that appear, and completely separable states, for example, just one of these 2 states is completely separable, or you can take this one of these Bell states or EPR states multiplied by one basis state. That will be an example of state like this. And this is a GHZ state, and W state is the state where you have at minimum 3 terms in the expansion in the linear combination. That's one example of a double state, but that's a class of states. So you can act by any local unitary. It might be a different state, might have very complicated forms. So there's the number of dimension of this Hilbert space is 9, so there could be more than 3 elements, but the minimum number of elements for W class is 3. And that's how it is different from the GHZ state. Okay, so this kind of states, this picture is actually similar to tensor network constructions. And here you can see that there is kind of Ryo-Takayanagi formula for this kind of states. And you can see this, for example, you can use replica trick and compute the entanglement entropy. So if you have a state like this, which has a number of connections, so there's a part which is connected between 2 sides and part which is disconnected, well, you can construct the density matrix. Now that's a reduced density matrix where you trace out this part B, which is shown by in green and red here in the middle. So these circles here, by the rules that I explained, they give this prefactor of d to the n over 2, and this is the result. This is the reduced density matrix. Then you can compute arbitrary power of this density matrix is given by the same diagram. The only thing that changes is the prefactor. So that's the trace of rho to the power k. And then you can compute the, again, the trace of this, and it is equivalent to a trace over a smaller Hilbert space. And which is to say that the entanglement entropy is defined by the minimum number of lines that connect the left and right in this system. So you can put it in this way. If you think of this diagram as something in three-dimensional space between two S2, then at some point you can insert another S2 which crosses the minimum number of lines. And then the entanglement entropy will be defined by the dimension of this Hilbert space. So this is just different colors here mean that I just separate the whole system into n and m points, and m points are connected with the right, and n points are not connected to the right. That's I mean, it can be arbitrary, split in n and m can be arbitrary. So if you have all of them connected, that's maximally entangled. If you have less, then this is, you can think of it as defining the rank of the matrix in the Schmidt decomposition of the representation of the state. In this case, the dimension of the Hilbert space, if you assume level very large, then it's given by Catalan numbers. And in the limit of large n, large number of points, that scales as, the entropy scales as 2n log 2, so there will be log 2 entropy for every line. So there's a way that I'll use later to calculate the entropy just by counting the lines. So if you have, here you have, for example, 6 lines, then there's 6 log 2 entropy for this initial state. That was kind of Ryota-Kuyanagi case, but this is not always true. So if you consider most complicated topology, then the entropy will not be given by the minimal area of the minimal surface here. And this is one example where you have this kind of chain. And if you consider this is something you can compute using the basis that I introduced earlier. You can consider the whole family of states by just taking Lth power of this combination by concatenating the same diagram many times. And here the entropy, you see that the entropy, except for a few values of k, so this is entropy as the function of k, especially for large k, the entropy decreases. And if you consider higher power of L, the entropy will be every time smaller and smaller. So eventually when k is infinite, you will only have delta function almost peaks here. So there will be only 3 points where the entropy is 1. And in the remaining part of the values of k, it will be simply 0. Or another example you can consider is this kind of topology. Here it's the opposite. So for large k, the entropy goes to the maximal value. But if you introduce more and more circles in these diagrams, you'll have the entropy will be smaller and smaller, and you'll have again somewhat similar picture here. So you can think of this more complex diagram as some kind of quantum corrections, because if you take the limit k equals infinity in Chern-Simons theory, this is a classical limit of Chern-Simons. So in this case, the Skene relation becomes simply, the braid group, this kind of diagram becomes simply a permutation. So this means that if you try to make a knot in terms of permutations, that this is actually not a knot. You can always reduce it to a collection of circles. And in particular, it is clear that in terms of the classification that was introduced earlier, this is just a separable state. You can just remove this circle in the middle. Here you can remove this circle, and this is the maximally entangled state. That explains the behavior of the curves, and you can sort of compute corrections to the entropy in this case. And as a function of k for large k, you will have this kind of expansions. Well, there are some other, in principle, yeah, I didn't mention that, but these initial types of states that I was considering, like these ones, I refer them as to connectomes, borrowing this terminology from neuroscience, where they map the connections between neurons. And the idea behind this state is just to choose, well, classify the entanglement by adjacency matrices of two graphs, of a graph, just counting connections, how many connections there are between two nodes of the graph, and how many connections are self-connections of the nodes. But there is, in this case, if you look at just simple diagrams like this, then in the classical limit, there will be no non-trivial topologies, and all states will be these connectome states with very simple topology. But if you go, but there are some non-perturbative states, and these non-perturbative states, they're related with non-trivial three-dimensional topology. So what you can do, you can consider topological defects in the bulk in this S3, and in particular, it can be globally this S2 cross S1. This can be shown by, well, achieved by cutting solid torus and then flipping the role of contractible and non-contractible cycles. You can check what happens with the entropy, and again, in this case, because of this topological defect, the Ryuta-Kayanagi formula will not work, so the minimal area of the minimal surface formula will not work. So just to demonstrate a few properties of this approach, you can use this kind of picture to compute. It doesn't change pages anymore. So you can study these different properties of entanglement in this case. I think now it works. Well, let me just quickly demonstrate how you showed this subadditivity property of the entanglement entropy. So if you have a system which has two subsystems, A and B, this is actually worse, I think. Then the entropy of the union of A and B is less than the sum of the entropies of A and entropies of B. And here you can check this by computing, as I said, for the entropies, you just compute the number of lines that connect different sides. So you have A and B and the complement AB bar. So each of them has some number of lines attached. So if you compute the number of lines, then there's a simple relation that you can check, that the number of lines connected to A and A plus number of lines connected to B is equal to the number AB bar plus twice the number of lines connecting A and B. And then it is trivial to show that this is greater or equal than NAB bar. And what is mutual information in this case? So it is defined as the sum of SA, SB minus SAB. So that's exactly twice the number of lines. So that mutual information is just the number of connections between A and B in this picture. You can continue and do the same thing for strong subadditivity. If you calculate this for this conic tone states with the simplest topology. You can show that counting of lines is equivalent to computing the entropies. But it's more difficult to show this for arbitrary states if you have non-trivial topology. I haven't tried this. But this kind of analysis can hint and indicate some other types of inequalities. So you can first try to guess the inequalities by counting the lines, and then check whether this is true in quantum mechanics. So in particular, the monogamy of mutual information, well, this, in terms of line counting, is actually saturated. So because this counting actually, this calculation of this derivation of inequality is very similar to the calculations that were done in holography, initially by Hedrick and Takayanagi, but by others as well. I think that in this case, you will derive the same inequality as in the case of holography. Another example is a case of entanglement measures. And if you want to understand how to detect, for example, a three-way entanglement, let's think there is a state, just schematically, it has three parties, A, B, and C. And the question is whether it's a generally three-partite entangled state, or is it biseparable? If you compute density matrix, so you can connect, for example, the density matrix of the subsystem A, you just connect B and C, just take the square of two density of two wave functions, connect B and C parts, and then if you're lucky, and then A is not entangled, then you can detect that the state is not generally three-partite entanglement. But in principle, you need to compute at least two density matrices to detect the three-way entanglement. There is a quantity which is called 3-tangle, which can distinguish the GHZ type, but it is 0 on W, so it does not detect W entanglement. Oh, right. Okay, but you can notice that in case of the density matrix and for Neumann entropy, the idea basically was to determine the weak link in this topological picture, and if there's absence of connection, then in this case the state is unentangled. So you can just take this state and make this kind of ladder, and if any of the parties A, B, and C are not connected, then this will be detected by this kind of ladder if you compute the analog of the von Neumann entropy. So it is just a way to determine the weak link. And if you think of the minimal area formula, then indeed the result should be somewhat defined by the part of this ladder where the link is the weakest. So that would give you this result. So here just a simulation for many 3-qubit states, and here you can see a GHZ state, a W state, and here the separable states, and that's the vertical axis is the 3-tangle, and horizontal is this alternative ladder invariant, and you can see that for this ladder invariant, for some reason W is not the strongest one, and there are more states which have more three-partite entanglement in terms of this this definition. Okay, so now I'm coming to the last part, and I'd like to discuss the black hole evaporation. So first, I want to introduce quantum teleportation in this topological language. In quantum teleportation, Alice has a certain state, unknown state, and she shares also a maximally entangled pair of qubits with Bob. So in order to transfer the state of Alice to Bob, she needs to make a measurement, and well, in terms of topological terms, it's just connecting all the lines in this way, and then the state is just transferred to Bob in the original way. I mean, this is some non-trivial measurement. You might wonder what really this kind of measurement means, and there is a more detailed version of that in quantum information. This is the basic protocol, quantum protocol of quantum teleportation, where you need to apply certain gates and then do some measurements, and this measurement has to be communicated to Bob. Then after that, Bob needs to apply certain transformations, and then he recovers the state. And you can nicely, represent this kind of protocol in terms of just braiding the lines. So if there is unknown state, you apply first this kind of braiding. Then the measurement means projecting on the basis, in this case on this non-orthogonal basis. There are different choices. Depending on the choices that is done, Bob will need to apply certain braidings on his side. It's just the cylinder means possible options for Bob to do. And then you can check that the states will be transported exactly in the original state. So the idea is to apply this for the teleportation of information from the interior of the black hole. So in the information paradox, what we have is the problem is related to production of the Hawking radiation, in which one pair of particles fall inside in the interior and the other goes to infinity. And then an observer that collects the Hawking radiation at the infinity at some point will discover that after the complete evaporation of the black hole, there will be a number of entangled particles. So this is not compatible with the unitarity. And as was explained in the lecture by Juan, another way to tell this is that if you compute the entropy of the radiation of the black hole separately, they will not follow the Page curve, which is compatible with the unitarity. So here the proposal is to, let's consider just a discrete bit model of a black hole where you have a bunch of bits. So one half which is called interior and the other one called exterior. And then let's assume that there is, there should be some interface between two sets of particles, and this interface should be penetrable one way for physical particles, and unphysical virtual particles can cross it in either way. And let's assume that there is certain interaction of particles, in this case just usual R matrix, for which we have this skein relation. And we will interpret this skein relation, so the scattering means that two particles either not interact at all, or there is an exchange of virtual particle. In this case, this exchange, because this diagram basically means there's no particle exchanged. And so virtual particles can cross the horizon, so in principle we can draw the horizon line between these two lines of particles. All right, so here is the diagram of evaporation. In this case, we start with some certain state. So these blue lines in the bottom, they represent some initial state for the interior of the black hole. And we have to assume that this is some kind of scrambled state. So scrambling here is represented by this idea that, all states which are close to the horizon, so horizon is this dashed line, are entangled with some other states which are deep in the interior. And since it's a kind of topological setup, I can draw horizon the way I like, and this is the most convenient way of drawing it, compatible with this idea that some particles can cross it, or the physical particles can cross it only in one direction. So in this first moment of time, there's some interaction happens, and in particular, there's non-trivial scattering happens, and a pair of Hawking pair is created outside of the horizon, and one of these particles falls immediately back inside the horizon, and the other goes to infinity. This process continues, but the particles that fell into horizon, it actually interacted again with another particle, and the result was two particles again outside of the horizon, and the story repeats. One falls inside, and the other one goes outside. So first, initially, you can check that if the observer at the infinity will try to measure the entanglement of these particles at infinity, so the observer will see that these points here are connected to points in the boundary, so which means there's entanglement, and this entanglement will increase. So here, there's blue numbers in blue on the right side. They just count in the number of lines that connect interior and exterior. And initially, this number grows. So it goes 0, 1, 2. But then at some point, when this interaction and reconnection happens inside the horizon, what happens that, well, these two states actually become correlated. This correlation now means that these two particles are correlated. So it is quantum teleportation occurred, let's say, of these two particles to the exterior. And well, then the process will continue, and you will see that there is no way actually for the entropy of the radiation to be more than the entropy of the black hole. Here, the entropy of the black hole is just the number of the degrees of freedom inside, which is counted just simply by the number of lines inside the horizon. So this number always bounds the number on the right from above. So in this way, what you basically should see is that the number on the right is increasing initially, and then it can fluctuate a little bit, but always less than the number on the left, and eventually it will be 0. Okay, so that's, although I do not make a plot, but I hope that this is clear, that this is the behavior of the page curve and consistent with the unitary behavior. Okay, so that's my conclusions, and I introduced topological description of quantum mechanics. And the idea is that this is a very intuitive way of describing things, and also, well, hopefully, well, it certainly helps understanding certain things we already know, and hopefully it can help to understand things that we do not understand that well. Well, it's not connected directly with gravity, but due to this connection between Chern-Simons and holography and ADS-CFT in lower dimensions, it might be useful to understand what's going on in the holographic description. So one attempt that was made here, it was build a small toy model of information extraction from the interior of the black hole. Thank you very much.
Questions?
It was a super beautiful talk. I like very much. One question, if you go back to this idea of the page curve, I mean, since you were already mentioning, so it's ADS3, you can write gravity as a Chern-Simons, but then it's a bit hard to see how you get at dynamics. I mean, these things don't really travel at a finite speed. Yeah, I mean, so I was just wondering, can you explain one more time your idea how you get the page curve, because I don't quite see how the time evolution.
So, well, the topological theories, we say that they are trivial. There's no local dynamics, so there's no particles moving at certain speeds. But this is not exactly true. So these are, they should be viewed as some discrete version of quantum mechanics, and where, well, basically the lines, they are the kind of spins at fixed positions, and the only thing you can make is flip the positions of the particles. And all the evolution also happens in time steps. And these time steps defined basically by the times where you apply the evolution operator. So in this case, you have to, it is like a computer, so it's like an algorithm. You just run, you have to choose Hamiltonian, which means a sequence of gates you will apply to your initial state. So here I just simplified the picture and said that the interaction only exists next to the horizon. So my Hamiltonian was such that there was this sequence of application of this scattering matrix to the near horizon states.
Yeah, thanks very much. If I may ask one other question, at the beginning you mentioned the Jones polynomials. Did they enter anywhere?
Which one?
The Jones polynomials you mentioned.
Jones, yes.
Did they enter at the end now in this analysis that you presented towards the end?
They do enter, in fact, in some way, these coefficients that you would calculate here in the expansion, because, well, to calculate the coefficients in the expansion of a state in the basis, you need to compute overlaps. And to determine these coefficients, you have to calculate overlaps with those states, that basis states that I showed in the beginning. So that means that you will always, to compute these amplitudes will always be this kind of diagrams, but generically more complicated, some knots, and this is where the Jones polynomials enter. So all these coefficients, I mean, you might not even notice if you use this kind of simple prescription and you work with simple states, but if you look at something more complicated than these states, then of course.
More questions?
You had these examples where the interactions were lowering the entanglement entropy.
So this is kind of, it is somewhat initially counterintuitive, saying that if you add more, well, let's call it perturbation like this, additional lines, or maybe lines like this, then you call it tangling, so you expect to have more entanglement in this case, but it's actually the opposite. And the reason for that, the way of thinking about this, is that well, making this diagram more and more complex means the space is less and less connected. So it means that you, especially in this case, you basically, this lack of connectivity is adding these defects, which is like adding holes to the space. So if you have infinitely many holes, then your space is essentially disconnected and there's no entanglement.
I mean, to lean the order, you found that it looks like minimal surface, but then the interactions, was it here? Yeah, minimal area. I think. Yeah.
Well, so this is, yeah, for this state in blue, which is essentially, as I said, because in terms of this conic tone classification, then the lines on the left, well, only two lines connect left and right, so this means that it's not entangled. And this is asymptotically in the classical limit. When you take the classical limit of this, you can forget about the circle, and the entropy goes to 0. Or in the second case, when the circle disappears, you return to this log2 entropy of the pair of the two qubits.
So would you say that in this case, Ryuta Kanayaki would not hold?
Well, it holds in the classical limit. It holds exactly. So in the classical limit, you will not have this additional defects, and the formula will hold exactly. But if you add the defects and you depart a little bit from the classical limit, then there will be finite k, and these are the corrections. So here, this is correction to 0 entropy. This is correction to this log2 entropy. So, so these kind of states, here they're kind of classical states. That's why I would like to say that they're analogous to classical geometries, while these are quantum states. So they are simply linear combination of classical geometries. So one thing actually I forgot to mention here, that in this diagram, I think you can also explain what island is in this term. So island is, well, you have this void that appeared inside the horizon once the two states are teleported. So in terms of radiation, this is the island that initially formed, and more states teleported, this island will grow and eventually will fill the whole interior of the black hole. Sorry, I answered actually the questions that you didn't answer, but that was the point I wanted to mention as well.
Any more questions? I had a question. If you apply level rank duality to this kind of construction, like
which duality?
Level rank duality. How all this entanglement will change?
Well, it's not supposed to, because well, the conjecture is that the Chern-Simons theory should be the same, but you have to work harder, because in this case you will have to work with SUN instead of SU2, and then it's also possible, but yeah, I didn't check, and in principle should work as well.
Okay, so if there are no more questions, let's thank Dmitry again. And before we leave, let's thank the organizers for